Video, we're going to do a complete regression analysis. We're going to try to predict house selling prices. In this case, we have the results of a regression analysis for 100 homes that relate the selling prices in dollars to the size of the house measured in square feet. And the question is whether size is a good predictor of selling price. We see that we have a regression scatter plot predicting the house price with the house size. So price is on our y-axis, and the house size in square feet is on the x-axis. We also have the parameter estimates. So the intercept here is A for our prediction equation, and our slope here is B for our prediction equation, as well as the results of our inference. We're going to start, though, by looking at the scatter plot. We see that for the form, this is a linear relationship because there is no obvious curve or nonlinear relationship. The direction based on the points is positive. As the size of the house increases, the house price tends to also increase. The strength of the relationship is moderate to moderately strong. That is, around this red prediction equation, we see that there is a reasonable amount of spread. The points aren't super tightly clustered, but they also aren't extraordinarily scattered around the line. If we knew what the correlation was, or if we knew what the R squared was, or even the RMSE, we'd be better able to explain the strength. Finally, we want to look for any anomalies. In this plot, we have some possibly unusual observations. For example, this house that is about 5,500 square feet also sold for about $700,000. That is outside the general trend of the data. It is unusual in that most homes that were about 5,500 square feet did not sell for that much money. Similarly, we have this point that is unusual on the x-axis. Most of the homes in the data set are not as big as 8,000 square feet. This is a big gap in the data. So I would be concerned about those 2 points that I highlighted. So we have two possible unusual observations. Because we don't have any other information about those 2 points, we can't just go ahead and exclude them, but we do have to recognize that they may be exerting undue influence on our regression equation. Our fitted line is y hat equals a plus bx, where y hat is the predicted selling price for homes at a specific value x, the house size. Based on the regression output in our parameter estimates table, y hat is $117,785.94 plus $52.43 for each additional square foot. So this is A plus BX, which we got from our parameter estimates table. The question now remains, is size X a useful or good predictor of sales price Y? We're going to do this using a hypothesis test. Our null hypothesis is that sales price is not a good, that size is not a good predictor of selling price. That is, that there is no linear relationship between price and size. The alternative hypothesis is that size is a useful linear predictor. And that would just be that there is a linear relationship, or that the slope is not zero. Notice, we are not stating specifically that size is a useful positive predictor or size is a useful negative predictor, just that size is a useful linear predictor. And that's because the question up here in the problem is size a good predictor? We're not asking about a specific direction, and so our alternative hypothesis there must therefore be two-tailed. We have to also remember to define our slope, our parameter, in context. So in this case, beta is the true average change in the house sales price for each additional square foot in size. Remember, the population slope tells us the true average change in the response for each additional unit in the explanatory variable. In this case, the response is the house sales price, and the explanatory variable is the size. The next thing we want to do is check our assumptions. In this case, we only can check some of the assumptions because we only have so much information. But we can see that the linear model is appropriate because the scatter plot indicates a linear form. If we saw a nonlinear form in the scatter plot, then we would not be able to use a linear regression model. We also can assume a random sample of homes. In this case, we're not told that we have a random sample of homes, so this is a true assumption. We do know, however, that we have a quantitative response and that we have a quantitative explanatory variable. Both the sales price and the size of a house are quantitative. It would make sense to talk about the mean sales price of homes as well as the mean size of homes, and so therefore they're both quantitative variables. The last two assumptions, which we have not talked about how to check, are that the response is normal and that it has the same standard deviation at all values of the explanatory variable. There's another video, regression diagnostics or residual diagnostics, that talks about how to check those two assumptions. So now what we want to do is go into our mechanics. We need a test statistic. Our t-test statistic, we would find this by taking our sample slope, subtracting off the hypothesized value, and dividing by the standard error of our sample statistic, which in this case is the standard error of b. If we look in our output, we see that our sample slope is 52.43 and the standard error of our sample slope is 6.61. We remember that our hypothesized value for the true population parameter is 0. So we will plug that in, and we would do 52.43 minus the hypothesized value of 0 over the standard error of 6.61. When we do all of that, the 52.43 minus divided by the 6.61, we're going to get a t-test statistic of 7.93, which JUMP calls the t-ratio. This is my t-obs. It is a ratio of our estimate, our sample slope, over its standard error. So this is going to be b minus beta over the standard error of b. This ends up being 7.93. It says our sample slope is 7.93 standard errors greater than the hypothesized slope of 0. We've interpreted these sample test statistics before, and we said that if we had a t-score greater than 3 or less than -3, then we would consider that to be a large test statistic. In this case, we have a t-test statistic of 7.93, and that is pretty big. Our p-value is provided by JUMP. Because we did a two-tailed test, remember our alternative hypothesis is that beta is not equal to 0, we can use the p-value from JUMP, which they call probability greater than the absolute value of t. that absolute value makes it a two-tailed p-value. So if we look in our jump output, the probability that we get something greater than a positive 7.93 or less than negative 7.93 is a very, very small probability. In fact, our p-value is less than 0.0001. In fact, this means that if there is no relationship, in fact, if there is no linear relationship between sales price and size of a house, or size of houses, the probability of obtaining a sample statistic, like a sample slope, for example, at least as big, or at least as unusual as ours being this 52.43, is really small. It's less than 0.0001. If there's no relationship between house size and sales price of homes, we're going to observe a slope like this, or even more unusual, less than 1/100th% of the time. Now let's interpret this sample slope. This sample slope of B equals 52.43. This says that for each square foot a house increases, we predict the house price to increase on average by $52.43. So we're paying on average $52.43 for every additional square foot a home increases by. So if you were to compare two homes and one was 1 square foot larger than another, we would expect that larger house to cost $52 more. Now most homes don't differ by only about 1 square foot. Most homes differ by maybe 1,000 square feet. So if we were to compare a house that is here at 1,000 square feet and another house that's here at 2,000 square feet, that difference would be $5,200 on average in terms of price. And that makes sense. We would expect to pay about $5,200 more for a home that is 1,000 square feet larger than for another home that is 1,000 square feet smaller. So thinking about things in terms of 1 square foot at a time is kind of hard. But if we think about homes in terms of 1,000 square feet at a time, that makes things a little easier to interpret this slope. So now the question is this a big effect? If we're paying $52 per square foot, or $5,200, or $5,243 per 1,000 square feet, is that a large effect? Is that meaningful? We want to think about the size of this effect when we're thinking about interpreting the overall results. We have a very small p-value. So the p-value is itself telling us that we have strong evidence against that null hypothesis. We have strong evidence against the null hypothesis, and we furthermore have 100 homes, a reasonable sample size. And I'm going to say that this is a reasonable, or at least a moderate effect. The slope isn't 0, it's not very close to 0. We are seeing a reasonable change in the response for each 1 unit increase in X. If you tell me that I have to pay $52.43 every time we add on another square foot to a home, that means something. So all of this together tells me that there is strong evidence of a meaningful relationship between sales price and house size. I apologize for spilling over into this other space. The p-value is very small. That's our small evidence. The sample slope, our effect size, is large. So we have strong evidence because of this sample, this small p-value, and the effect that we have detected is fairly large. So it's not just that we have strong evidence that there is a non-zero slope, but the non-zero slope we have identified is pretty big. So now let's look at it this way. A builder has claimed that the selling price increases $100 on average for every extra square foot. What do you conclude about this claim? This builder is saying that the true slope equals $100 per square foot. Do you buy that? Do you believe that this is a reasonable claim? Now we could go and we could test a null hypothesis, or we could build a confidence interval. I suggest we do the latter. Let's build a 95% confidence interval for beta. Now remember, every confidence interval is of the form stat plus critical value times the standard error of that statistic. In our case, our statistic is B, our sample slope. We're going to use a t with n minus 2 degrees of freedom critical value, and the standard error of the statistic is just the standard error of our sample slope B. Our sample slope, just as before, is 52.43. Our critical value we're going to have to get from jump. So remember how to get a critical value from jump. We choose the distribution we're interested in. We select T. In this case, we have 100 total observations, meaning that we have n minus 2, or 100 minus 2, which is 98 degrees of freedom. If we want a 95% confidence interval, that means that we have 95% chance in the long run over repeated intervals of capturing the true slope. So that 95% is a probability. So we're going to input our 95% as a probability to calculate our t critical value. We're going to make this a central probability because we're putting all those values in the middle of our interval. So I'm going to make a central probability, and I'm going to put 0.95 in the middle, and that means my t critical value is 1.98. The standard error of my slope is the same standard error that I used for my hypothesis test, and that is 6.61. Altogether, I now have my sample statistic, 52.43, my t critical value with n minus 2, or 98 degrees of freedom, which is 1.98, and my standard error, which is 6.61. This 1.98 times 6.61 is my margin of error. The lower bound on my interval is 39.34, and the upper bound on my interval is 65.52. Notice that this interval is in dollars, because I'm dollars per square feet, because I'm estimating the slope. So the smallest I believe my slope to be, based on this sample, is $39.34 per square foot. And the largest, or the steepest, I'm willing to believe my slope to be is $65.52 per square foot. And so based on this builder's claim, I don't think that claim is reasonable. The builder is claiming that the selling price increases $100 per square foot, but this sample just doesn't support that. This sample supports a maximum slope of 65.52. And not only that, that sample slope, that maximum sample slope, is really far away from $100. So this builder is way off on his claim as far as my sample is concerned. My sample doesn't support anything near $100 per square foot in terms of a slope. So I'm going to interpret my interval. With 95% confidence, the true mean change in the sales price for each additional square foot of a house is contained in the interval 39.34 to $65.52 per square foot. I don't know if this interval actually is containing that true mean change or that true slope. The builder could actually be right, and I could just have a sample with an unusually low slope from that true population.